Section 2.4 and 2.5. I'd like to combine these two sections because they both deal with differential equations that do not fit one of our established forms, but they're differential equations which can be transformed into one of those established forms using some sort of substitution. So our strategy is in this lecture is to start with an ODE that is not linear, it's not separable, it's not exact, to make a substitution according to some prescribed process or formula, and then that substitution will transform our original ODE into one which is linear or separable or exact. That will then enable us to use the techniques from the previous three sections to solve the new ODE, and then as a final step, we'll undo our substitution and retrieve a solution to our original ODE. This is a relatively common technique, and this happens a lot in ordinary differential equations and when solving partial differential equations. In this section, we're just going to look at two specific examples of this strategy. The first example will involve ODEs that have this specific structure, as stated here. Most of this ordinary differential equation looks like a first-order linear ODE. Specifically, the left-hand side certainly does, and even this q of x on the right-hand side. But it's this y to the n term which violates the requirement of linearity, and so that's the term that makes this ODE non-linear. This type of ODE is called a Bernoulli equation, and as I just explained, our approach will be to make a substitution in this differential equation that transforms the original ODE into a first-order linear ODE. And then once we have a new ODE, which is first-order linear, we'll solve that using the techniques from previous sections. Specifically, the substitution that we need to make is, we can think of the substitution as being v will be set equal to y to the 1 minus n, or we could think of the same substitution as setting y equal to v to the 1 over 1 minus n. These two forms are equivalent if you do the algebraic manipulation between the two of them. So in my first order ODE, everywhere I see a y, I'm going to make this substitution. And then note that we'll need to make a substitution for y prime as well. And as I've stated here, that will require an application of the chain rule. But making those substitutions will transform my original ODE, which is in terms of y's, into a new ODE, which is in terms of this new variable v. And as you'll see, while my original ODE is not linear, the transformed new ODE will be first order linear. Let's take a look at the first example. Just a word of warning, there are a lot of steps involved in these problems, so make sure you keep track of the different stages that we're following as we go through our solution for this ODE. Here I've started by making a couple steps of algebra just to rework the structure of my ODE, and it's easy enough to identify comparing this particular example to the original form stated above that the n involved in this particular equation is 3. That indicates that the substitution that I want to make will be v equals y to the negative 2. Or, if we want to solve that for y, we would get y equals v to the negative 1/2. I could, of course, rewrite this as 1 over the square root of v, but because of the calculations we're going to be doing, and when we substitute this in, it would probably be a little cleaner to keep it as v to the negative 1/2. As I noted above, we'll be required to also make a substitution for y prime. I should remind myself here that the independent variable is x, and both y and v are acting as dependent variables. So in order to calculate y prime, I'll apply the derivative with respect to x to the expression v to the negative 1/2. And I will apply the power rule to get negative 1/2 v to the negative 3/2, but then I have to remember to multiply that by a v prime. Recall that v is an unknown function of x. And so if I have an expression like v to the negative 1/2, that when I differentiate it, I will apply the power rule as appropriate, but then I have to multiply by the derivative of v to account for the fact that v is a function of x. So let me just reiterate the substitutions that I'm going to make. Provided them here in orange. And now I can substitute according to those equations into my original differential equation. As I expected, this transforms my original differential equation, which is in terms of y's and x's, into a new differential equation in terms of v's and x's. The value of this substitution isn't obvious yet. Let me do a couple steps to simplify this so that I can see exactly what type of differential equation I'm now dealing with. Here I've multiplied the entire equation by v to the negative 3 halves. That is, I multiplied by this term, v to the negative 3 halves, by all the way through the entire equation in order to just clear out that term. Next, let me just clear this fraction on v prime. And after that algebraic simplification, I can recognize that in terms of the dependent variable v, this differential equation is first order linear. So the substitution that we made has transformed my original differential equation, which was not linear, into a new differential equation, which is linear. This enables me to apply the technique from a couple sections ago in order to solve this differential equation. You will hopefully recall that the first step is to construct a mu of x, an integrating factor that I'll multiply through my entire equation. And here are the steps required to generate that mu of x. Now I'll multiply my entire equation by this mu of x. And now I know that the left-hand side will have the structure of the result of a product rule. Next, I'll integrate both sides. And finally, I'll multiply by x to the fourth in order to solve for v. So at this point, we have solved the first order linear differential equation that we had encountered, but this is not my final solution. Recall that I have made a substitution from y to v's, so this is the solution to the differential equation that was in terms of v's. My next step is to undo my previous substitution so that my solution will be back in terms of y's. At this stage, I have an implicit expression for my general solution, but if I want to push a little further to have an explicit expression, I can simply do the step or two of algebra required to solve for y. So here I have my final answer. This is an expression for the general solution of my differential equation. Let's try that same solution technique again by taking a look at example 2. In example 2, our differential equation has a couple unknown constants, r and k. Both r and k are positive, and we'll just leave them constant and manipulate the differential equation as necessary. Just as a note, this particular differential equation has significance in the context of population modeling. So this is actually an important differential equation in that specific context. I'll once again start by algebraically manipulating my differential equation so that it has the standard form. The left-hand side feels like a first-order linear differential equation. The presence of the y squared term on the right-hand side is what prevents this from being linear. And from that y squared term, I easily identify that the n at play in this example is 2. Using the prescribed form of the substitution, I'll sub in v equal to y to the 1 minus 2. It's the same as y to the negative 1. And algebraically working with v equals y to the negative 1 yields y is equal to v to the negative 1. As in the previous example, I'll be required to make a substitution for y prime. So here I've calculated the value for y prime, once again bearing in mind that v is a function of x. So when I differentiate a v term, I have to remember to multiply by this v prime term. So here are the two substitutions that I'll make into my original differential equation. Making those substitutions yields this new differential equation in terms of v. And once again, to start the solution process for this differential equation, I'll multiply through by, in this case I'll multiply by v squared. I guess I'll multiply by negative v squared, just to clear out this coefficient term and clean up the structure of this differential equation a little bit. This reveals that this differential equation in terms of v's is first order linear. That's of course not a coincidence. Any Bernoulli equation in which we've made the appropriate substitution will turn into a first order linear differential equation. So I'll now use the techniques from a couple sections ago in order to solve this first order linear differential equation. I first solve for my integrating factor mu. Note that I've chosen to use t as the independent variable. In the original differential equation, the independent variable isn't present, so I could interpret it as being x or as being t. Because this is used in the context of population modeling, I'm accustomed to using the independent variable t for this type of equation. I next multiply the entire equation by the mu of t that I just constructed. And then I follow the necessary remaining steps in order to be able to solve for my solution v. Recall that this isn't my final answer because I still need to undo the substitution I made a second ago so that my final answer will be in terms of the original dependent variable y. Completing the necessary steps yields this final expression for our general solution in terms of y. As I mentioned, this is an important equation in the context of population modeling, and this function is actually what's known as the logistic equation, or this model is known as logistic growth. Next, we'll look at an example of another type of differential equation and another substitution, which will transform this type into a form that we can solve. This technique requires that our differential equation have a very specific structure. As stated here, it says that our differential equation must have the form y prime equals capital F of y over x. This notation is not meant to indicate that the right-hand side is any specific function. It's simply meant to indicate that the derivative can be written in such a way that the right-hand side is an expression where every variable that appears on the right-hand side appears in this specific ratio. So every variable that appears on the right-hand side will appear as a ratio of y over x. This type of differential equation is called homogeneous, and I've provided a couple of examples. In this first differential equation, there's actually a typo. I've included these terms twice accidentally. But notice that in this differential equation, everywhere a y or an x appears, not the y prime, but the variables y or x, they appear in this ratio, y over x. The same is true in the second differential equation. In this third differential equation, that doesn't initially appear to be true, but you can check that if you were to split this into two separate fractions and do some simplification, you would have ratios of y over x. So as this structure suggests, the substitution that we'll make in these differential equations is to make y equal to y over x. That's equivalent to setting y equal to x times v. As you will see in the example we're about to do, completing this substitution will transform our original differential equation into a separable differential equation. And I now notice another typo. This is not the differential equation that I wanted to solve here for example 3. So let me cross this one out and instead just write the differential equation that I was expecting to try to solve. This is the differential equation that I meant to put here as example 3. I apologize for the typo. So the structure that we're looking for in this type of differential equation is that every appearance of the variables is in terms of the ratio y over x. That's not exactly true at this point. So my first step will be to somehow manipulate this overall right-hand side so that all of the variables will appear as a ratio of y over x. I can accomplish this by multiplying in the numerator by 1 over x, and then in the denominator similarly multiplying every term by 1 over x. This does yield a right-hand side that has the necessary form where the appearance of my variables always occurs as the ratio of y over x. So now I'm ready to make the necessary substitution. We're always going to substitute in v equals y over x. That's equivalent to y equals x times v. And in my differential equation, remember my left-hand side is y prime, or dy dx. So I'll need to calculate y prime of this substitution. And I have to recall that v is an unknown function of x. So when I apply the derivative to this expression x times v, I do need to apply the product rule. And when I'm differentiating this v, I need to indicate I've done so by including a v prime term. So these are the two substitutions that I'll make into my original differential equation. And these substitutions yield a new differential equation with this structure here. Remember that on the left side of the differential equation I have dy dx, so I'll make that substitution. And on the right side of the equation, my variables appear in these y over x ratios. I know that I'm going to sub in v for that ratio, so this is what my right-hand side becomes. I'll now take whatever steps are necessary to solve this differential equation for v. Here I've done some algebraic manipulation and simplification. I've isolated my derivative dv dx. It still may not be totally clear, but this is a separable differential equation. And I can demonstrate that by separating the derivative dv dx. And then I'm going to move this v fraction over to the other side. I'm going to multiply by its reciprocal. This will give me... Now I can see clearly that all of the v's have been moved to one side, all of the x's moved to the other, so this is a separable first order ODE. You'll recall that to move forward to find the solution of this, I just introduce an integral on both sides. Now I need to do whatever is necessary to evaluate the two integrals I'm confronted with. The integral on the right-hand side is very straightforward. It's simply going to be the natural log of x. The integral on the left-hand side is a little bit more tedious. So let me just pause the overall problem and solve the integral on the left-hand side. I'll first split the fraction into two separate fractions and then two separate integrals. And this second integral looks like I can apply u substitution, but to evaluate this first integral, I believe I'm going to have to use partial fraction decomposition. Here are all the steps necessary to enact partial fraction decomposition on this fraction 1 over v squared minus 4. It might have been a while since you've seen this process, but hopefully you remember these details, and so you would be able to complete this process if one of the integrals that you're confronted with requires it. Let me go back to the integrals that we were trying to solve on the previous page. Now I can evaluate these integrals. I've sort of run out of room, but hopefully you can see the different details here. And I've finally evaluated all of the integrals on the right-hand side. Scrolling up to look at our original problem, we see that these orange integrals are all what we need on the left-hand side of our equation. On the right-hand side, as we've already mentioned, we'll simply have natural log of x. Let me go ahead and write that out. And there actually is some simplification I could perform on the left-hand side in order to combine these logarithms, but I will be satisfied with an implicit expression for our general solution, and so I'm not going to try to pursue any simplification. The last thing I need to do is to undo the substitution that I had made earlier in the problem so that my final answer is in terms of the original dependent variable y. And I will stop there. So that will be my final answer. So in this section, we've demonstrated two substitution techniques where we can make a substitution into our original differential equation and transform the original differential equation into a new differential equation that has a form that we know how to solve. As I mentioned, this is a relatively common technique, but for our purposes, we're just going to look at these two examples of these two solution techniques.